Hi everybody, so in this video we're going to begin with chapter 14, which is Integral Calculus 1. And these are the learning objectives for this chapter. So by the end of this chapter you should be familiar with integration as anti-differentiation of functions, calculating and applying definite integrals, finding the area under curves between two curves or between the curve and the x-axis, and also areas between curves. We're going to learn about anti-differentiation with a boundary condition. We're going to solve kinematic problems involving displacement s, velocity v, acceleration a, and total distance traveled. We're going to work with integration of polynomial functions, trigonometric functions and their inverses, and exponential functions. We're going to do integration by inspection, which is a reverse chain rule, use of partial fractions, integration by substitution, integration by parts, and repeated integration by parts, and finally finding volumes of revolution about the x-axis or y-axis. So 14.1 refers to the antiderivative. So what is the antiderivative? As the name implies, it is the inverse of the derivative. So if capital F of x is the antiderivative, if we differentiate that, we're going to get f of x, which is the derivative. And if we do the anti-differentiation, we would get to the antiderivative. Now look at this table to the left. Notice that if you have a function f of x that is 1, the antiderivative would be x. Now obviously if you do the derivative of x, you get 1. So the antiderivative of 1 would be x. Same thing with x. If you do the antiderivative of x, it should be x squared over 2, and so forth. So these would be all examples of a function and its respective antiderivative. Okay, so here we are now with example 14.1, and they ask us the following. Given the function f of x equals 3x squared, find an antiderivative of f of x. Okay, so in general, if we want to find an antiderivative of f of x, let's say that we have, in general, we have this. The derivative of the antiderivative, f of x, let's say that it gives us x to the n. So the rule to find the antiderivative would be adding 1 to n. So we would get x to the n plus 1, and then we'd also divide by n plus 1. So in this case, we have that f of x is equal to 3x squared. In other words, they want us to find an antiderivative that would give us 3x squared. But what we do then is simply apply the rule that I just showed you. So we would do that capital F of x would be equal to 3x to the 3 divided by 3, and this equals x cubed. Now this would be one example, but notice that they say find an antiderivative. The thing is that this x cubed could be accompanied by any constant. So normally when we find an antiderivative, we have to add the symbol for constant, which is the letter c. In other words, remember that if we do the derivative of this would just become 0. That means that when we find the antiderivative, we have to consider the possible existence of a constant. In the next slide, you're going to see a couple of things about notation of integrals. Now the integral would be finding the antiderivative. So for example, if you do the integration of f of x dx, then that would be capital F of x plus c. Equivalently, that means that capital F of x would satisfy the condition that the derivative of capital F of x, as you can see here, is equal to f of x, the original function. Then you can see this table below where you have some equivalence from integration to derivatives. So for example, the 3x squared that we just did before, integrating that would be x cubed plus c. And so forth. You have more examples that you can see for yourselves. Next, we will work on example 14.2. But before, we have to look at a couple of rules here for integration. Suppose that f of x and g of x are differentiable functions and k is a constant. Then a constant factor can be moved through an integral sign. That is, if you have integral of k times f of x dx, you can write that as k times integral of f of x dx. Then we have that an antiderivative of a sum or difference is a sum or difference of the antiderivatives. What that means is that we can separate an antiderivative or integral into separate terms if you have addition and subtraction. Now notice that this does not apply for multiplication. Multiplication of a constant, yes, you can take it out. But if you have multiplication inside the integral of functions, then this rule does not apply. It only applies for addition and subtraction. Okay, so here we go with letter A, and they ask us to find or to evaluate the integral of 3 cosine of x dx. So notice that we can rewrite this as 3 times integral of cosine of x dx. Then we can find the antiderivative of cosine of x. Remember that would be sine of x, right? Because the derivative of sine of x is cosine of x, so the antiderivative of cosine of x would be sine of x. So this is equal to 3 times sine of x, and don't forget to always add plus a constant c. For b, we can apply the rule for splitting the integral into its sums. So we could rewrite it as integration of x cubed, and don't forget to write dx, plus integration of x squared, and don't forget to write dx. And then here we do the antiderivative. As you recall, it was just adding 1 to the exponent. So this is going to be x to the 4 over 4. And don't write plus c, write it until the end, because if you have a constant here and a constant there, then you're just going to have the sum of those constants, which is also a constant. And this plus, in this case, x cubed over 3, and then plus c. Okay, next we have example 14.3, and they ask us to evaluate two integrals. So the first one says t cubed minus 3t to the 5, and both of those terms divided by t to the 5. Here, the easiest thing we can do is split this into separate expressions. So notice that we can rewrite this as the integral of t cubed over t to the 5 minus 3t to the 5 over t to the 5, and don't forget dt. And then we can simplify this. This would then equal the integral of t to the minus 2, and I'm going to separate it, dt minus 3 dt, or integral, sorry, of 3 dt. So then we can integrate this, right? What would it be? It would be, remember that we add 1 to the exponent, right? So it's going to be t to the minus 1 divided by minus 1 minus 3t plus the constant c. And this, of course, is equivalent to minus t, or minus t to the 1. We can write it as minus 1 over t minus 3t plus c. Then for b, we would proceed in a very similar way, right? We can split this, separate it. So we can say that this is the same as x over x squared plus 5x to the 4, x to the 4, and then this over x squared and dx. Then we can proceed to simplify this and separate the terms into different integrals. Then we can say that this is equivalent to the integral of 1 over x dx plus integral of 5x squared dx. And then we can just proceed to integrate. Now 1 over x, the integration of that would be natural logarithm of x. Now notice that with natural logarithm, we tend to write it as an absolute value. So natural logarithm of the absolute value of x plus 5x cubed over 3 plus c. Very well, so next you're going to find the topic of integration by simple substitution or a change of variables. So let's take letter A as an example. So letter A says that they want us to evaluate the integral of x cubed plus 2 to the power of 10 times 3x squared dx. So notice that it would be very difficult to expand this because it's to the power of 10, and then we would have to multiply it by 3x squared, and we would get a very large polynomial, and then we would do the differentiation, or the integration, I should say, the antiderivative, using the power rule that I talked about. It's much easier to put this integral in terms of u du. So that's the objective, to try to change the integral into terms of u du. So first we would have to identify what we are going to use u for. So u, normally we want to use it to substitute the value or the expression that is to a power. So in this case, let's say that u is equal to x cubed plus 2. But then we would also need the derivative of u, or du. So what's the derivative of u? It would be 3x squared times, or 3x squared times dx, the derivative of x. So notice that now we have everything necessary to substitute into this integral. We have x cubed plus 2, which will substitute this here. And we have 3x squared dx, which is du, that we're going to use to substitute this. So this ends up being the integral of u to the power of 10 du. And now we can do a simple integration using the power rule. So this will be equal to u to the 11 over 11 plus c. And then all we have to do is a subsequent substitution again. Since we said that u is equal to x cubed plus 2, we can plug that back in. And we can say then that this integral here, the original one, is going to equal x cubed plus 2 to the power of 11 over 11 plus c. Okay, so now we're going to do b. And b says find the integral of tangent of x dx. So tangent does not have an antiderivative because there's no derivative that will give us tangent. So we should rewrite this in terms of sine and cosine. So this is equal to the integral of sine of x over cosine of x. And then notice that we can rewrite this as, well, dx, don't forget that. Notice that we can rewrite this as the integral of 1 over cosine of x times sine of x dx. So the u substitution we can use would be u equal to cosine of x. And then we can say, well, let's make derivative of u. The derivative of u would be then minus sine of x dx. So that means that if we want to substitute this, right? Because this is what we have in the integral here, and we already have a substitute for cosine, which would be u. Then we have to rewrite this as minus du is equal to sine of x dx. So we have to consider this. So now we're ready to make the substitution into the integral. So it's going to be integral of 1 over cosine, but we're going to write it as 1 over u times the substitution for sine of x dx would be minus du. But this is just like multiplying by -1, right? So we could rewrite this as negative integral of 1 over u du. And this is a simple integration, which is just going to be negative natural logarithm of the absolute value of u plus c. So now we can substitute back because we said that u is cosine of x. So we can rewrite this as equal to minus natural logarithm of the absolute value of cosine of x plus c. And you can leave it like that if you want, but we can get rid of this negative sign because this is a logarithm, a natural logarithm. We can send this as an exponent. So we could rewrite this as the natural logarithm of cosine of x to the minus 1 plus c. But this is the same as 1 over cosine, right? Cosine to the minus 1 is 1 over cosine, and that's just second. So we can rewrite this finally as the natural logarithm of second of x plus c. So next is letter C, and it says find the integral or evaluate the integral of cosine of 5x dx. So when we do u substitution, we have to be careful as to what we make u. So let's not use cosine of 5x, but rather just 5x. So we can say u is equal to 5x. And then the derivative of u would have to be equal to 5 dx. So notice that we're missing this, right? For the 5 dx, we only have dx. But this is the same as saying that 1/5 du is equal to dx. So we can substitute dx with 1/5 du. But because this is a constant, we can just send it to the outside of the integral. And we can rewrite this one as 1/5 integration of cosine of u du. And then integrating this is easy because the antiderivative of cosine is sine. So we can just rewrite this as 1/5 sine of u plus c. And then finally, all we have to do is plug back the 5x, and it's going to be then 1/5 sine of 5x plus c. Okay, so for D, they ask us to evaluate the integral of cosine of x squared times x dx. So like in the previous case, we don't want to make u equal to cosine. In this case, we want to make u equal to x squared. Then the derivative of u would equal 2x dx, which is the same as saying 1/2 du is equal to x dx, and then we're ready to make the substitution. So this would be the same as saying the integral of cosine of u, and then when the 1/2, we can send a multiply ahead of the integral. So cosine of u du, and then this is just going to be 1/2 sine of u plus c, and then we just plug back in the x squared, and this is going to be then 1/2 sine of x squared plus c. Okay, and finally we have example E, which is the integral of E, or Euler's number, to the power of 3x plus 1 dx. So in this case, substitute for the exponent. So u would equal 3x plus 1, and then du would be 3 dx. In other words, 1/3 du equals dx. So now we're ready to substitute. So this is going to be the same as saying 1/3 integral of e to the u du. So this is going to be 1/3 e to the u plus c, but then we said that u is 3x plus 1, so this is the same as 1/3 e to the power of 3x plus 1, and don't forget the constant, plus c. So next we have example 14.5, where they ask us to evaluate the following integrals, and for these we're also going to be using the method of substitution. So for letter A, we have the integral of e to the power of minus 3x dx. So in this case, we do something very similar to what we did before. We would say, well, let's make u equal to minus 3x. Therefore, the derivative of u is going to be negative 3 dx, or negative 1/3 du is equal to dx. And then we're ready to substitute. So we can say negative 1/3 times the integral of e to the u du. And this is easy to integrate because it's just going to be negative 1/3 e to the u plus c. But then we have to plug it back in, right? The original equation, which was minus 3x in the substitution. So this is going to equal negative 1/3 e to the minus 3x plus c. Okay, so now we do b. And for b, we have the integral of sine squared of x times cosine of x dx. So always the difficulty is going to be what do we choose as u to substitute. So in a case like this, where you could do derivative of sine is cosine or derivative of cosine is minus sine, I would recommend you pick the one with the exponent. So u would equal sine of x. Therefore, derivative of u is cosine of x dx, and then we're ready to substitute. This would then be the same as saying the integral of u squared du. And the integration of this is simply going to be u cubed over 3 plus c, and then we substitute back in. We said that u was sine of x, so it's going to be sine cubed of x over 3, or 1/3 times sine of cubed of x, plus c. So next we have c, and c says integrate 2 times sine of 3x minus 5 and dx. So notice that this is a constant, this 2 is a constant, so we could rewrite this as 2 times the integral of sine of 3x minus 5 dx. So then u would simply be equal to 3x minus 5, but the derivative of u is going to equal 3 dx, or 1/3 du. 1/3 du is equal to dx. So now we're ready to substitute. We're going to substitute here, of course. So then it's going to be 2 times 1/3, so 2/3 integral sine of u du, and then the antiderivative of sine is negative cosine. That's something we have to be careful with, right? So this would be the same as saying negative 2/3 cosine of u plus c. And then we can just plug back in what we had for u, which is this expression, 3x minus 5. So this would just equal minus 2/3 cosine of 3x minus 5 plus c. Okay, so next is letter D, and it says integrate e, or Euler's number, to the power of mx plus n dx. So notice that m and n are just constants or numbers, so we don't have to really worry about that too much. And we can use for u substitution, because it's an exponent, we can say, well, u is equal to mx plus n, and then we have that the derivative of u would be m dx, or in other words, 1 over m du is equal to dx. So notice that we now have everything ready to substitute. So we could rewrite this as 1 over m integral of e to the u du, and this simply equals 1 over m e to the u plus c, and then just substitute back in. So this would be, the solution would be 1 over m e to the power of m x plus n, and don't forget the constant, plus c. This could be also considered a general rule for the integral of e to the power of a linear function. And then finally, we have example E, and it says integrate x times square root of x dx. And then it says if you plug 1 into the antiderivative, it gives you 2. So this is a hint. This here is a hint to find a value for c, for the constant. Then before you think about use substitution in this case, notice that if you have an expression like that, always try to simplify it, because x times square root of x is the same as saying x times x to the 1/2, and this is simply going to be x to the 3/2. So we don't really require any use substitution. This is going to equal then the integral of x to the 3/2 dx, and then we can simply use the power rule. So this is going to be equal to x to the power of 5/2, right? 3/2 plus 1, and then this divided by 5/2, and for now we'll say plus c. And then we can just rearrange this as, notice, as 2/5 times x to the power of 5/2 plus c. But here they gave us a hint to find c, because they say that when you plug 1 into the antiderivative, you will get 2. So that means that 2/5 times 1 to the power of 5/2 plus c is equal to 2. In other words, and we'll do this here to the left, in other words, we would say then that 2/5 times 1, so 2/5 plus c is equal to 2. So c would equal 2 minus 2/5, and this is going to equal 10/5 minus 2, so 8/5. C is equal to 8/5. So that means that in the end, with this information, we find that the antiderivative is going to be rewritten as this, right? And the antiderivative would be then 2/5 x to the 5/2 plus 8/5. Okay, so now we are in example 14.6, and this will be the last one on this video. And they ask us to integrate or evaluate each integral. So for A, we have the integral of the square root of 6x plus 11. But notice that we can write that as 6x plus 11 to the power of 1/2 dx. So then the only substitution we can possibly do here would be u is equal to 6x plus 11. So the derivative of u is going to be 6 dx. And then this is the same as 1/6 du is equal to dx. So now we can substitute. We can substitute for dx, and we can substitute for 6x plus 11. So we can rewrite this as the integral of u to the 1/2 du, and then we can just apply the power rule here. So this is going to be the same as saying u to the power of 1/2 plus 1, that would be 3/2. 3/2 divided by 3/2 plus c, and this is the same, oh, and I forgot the 1/6. So this times 1/6 here. So this times 1/6 here as well. So this is then going to be equal to 1/6 times 2/3 times u to the 3/2 plus c, and this is going to equal, notice that we can cancel this out, this will be 3, so this is going to equal 1/9 u to the power of 3/2 plus c, and then we can just substitute back in, so this is going to be equal to 1/9 6x plus 11 to the power of 3/2 plus c. Okay, so now B, where they say integrate 5x cubed plus 2 to the power of 8 times x squared dx. So then u would be 5x cubed plus 2, and then the derivative of u would be equal to 15x squared. And in other words, 1 over 15 du, I forgot the dx here. 1 over 15 du is equal to x squared dx. And we're ready to substitute for this, which is this here, and this, which is that there. So we can rewrite it as, and this time I won't forget, the 1 over 15 integral of u to the 8 du. And this is simply going to be 1 over 15 times u to the 9 over 9 plus c, which is equal to 1 over 135, that's 9 times 15, u to the 9 plus c, and then we just substitute back in, so we're going to get finally 1 over 135, and this would be 5x cubed plus 2 to the 9 plus c. Okay, so now we're going to do letter C, and for C, notice that we can say, well, let's make u equal to x to the 4 minus 8x plus 13. Then the derivative of u would be 4x cubed minus 8 dx. But we need to get to this expression here, right? X cubed minus 2. So notice that this is the same, du would be the same as writing this as 4 times x cubed minus 2 dx. Therefore, 1/4 du is equal to x cubed minus 2 dx. And now we're ready to substitute. So this could be rewritten as integral of u to the negative 1/5, right? Because it would be 1 over u to the 1/5. So u to the negative 1/5 du. And then, oh, and I forgot the 1/4. So 1/4 out here, of course, 1/4. And then this would be, the integral of this would be equal to 1/4 times u, and this would be minus 1/5 plus 5/5, or plus 1. So it would be u to the power of 4/5. 4/5, and this divided by 4/5 plus c, but this is the same as saying 1/4 times 5/4 times u to the 4/5 plus c, or 5 over 16 u to the 4/5 plus c, and then we just plug back in u. So this would equal 5 over 16, and then x to the 4 minus 8x plus 13 to the power of 4/5 plus c. Okay, so last but not least is example D. So I'll write it here. D is the integral of sine to the 4 of 3x squared times cosine of 3x squared times x dx. So the obvious option for u is going to be sine of 3x squared. Sine of 3x squared. Why? Well, because it's the one that is to the power of 4. So what's the derivative of u? What's du? So this would be then derivative of sine is cosine. So cosine of 3x squared. But we have to do the chain rule here. So this times 6x. So we have this to substitute for sine of 3x squared, right? And we have this, but notice that we have this extra 6. So we should say then that 1/6 du is equal to cosine of 3x squared times x, and I forgot dx, never forget dx. And then this is the expression that we can substitute with. So then we could rewrite this as 1/6 integral of u to the 4, which is sine of 3x squared, times du, which is all of this here, du. So then this simply becomes 1/6 times u to the 5 over 5 plus c, which is simply 1 over 30 u to the 5 plus c. And then finally, we just plug back in. So it's going to be 1/30 or 1 over 30 of sine of 3x squared to the 5 plus c.